Hey guys, how are you? Just want to talk you through this roller coaster energy conservation practical. So I'm just going to go through the prac itself, how do we collect the data, and then how we produce the write-up. So this is based on the law of conservation of energy. So just reading the preamble, energy cannot be created or destroyed, only transferred or transformed. We can investigate this effect using a simple mechanical system that will convert gravitational potential energy, or GPE, to kinetic energy, KE, and then back to GPE. By running a marble through a simple course, a roller coaster, we'll be able to assess how much energy was transferred and investigate the efficiency of a simple machine. So there's a few key concepts here, and I'll talk you through what we need to do. So if you're doing this in class, essentially what you're going to be setting up is a simple roller coaster. So we've got a diagram here. So we're going to have two retort stands with clamps, and we're going to attach those to some plastic tubing. And we're going to be moving, or I guess rolling a marble down our little makeshift roller coaster here. So the marble is on the inside of the tubing. So we'll start with the ball up the top. And what you want to measure with your ruler is the starting height, okay? So the starting height, even though in the diagram the line goes to there, realistically it's where you put the marble, where you're starting your roller coaster from. So we're going to measure that starting height and you'll be recording it. You'll be letting the marble go, and that will go through the roller coaster and it will go up and it will finish at a certain point before it drops back down. You want to record that finishing height. So you're going to have to kind of look where it finishes and approximate that and then measure that with your ruler. An important thing to note is that we're going to have to record the mass of the marble using the correct units. And those units are going to be meters, because for our formula, we need the mass in meters. That's the standard international, or SI, unit for meters. We're going to record the starting height of the marble, release the marble like I said, record the finishing height, and we're going to repeat that 2 additional times to get a sample size of 3 so we can calculate an average, because that reduces our effect of random error, which is really important in a scientific experiment. And then we're going to be replicating the steps 2 to 6, or replicating the experiment using 2 different tracks. And you can make ones, you don't have to make them like this, but these are some examples. So if you did this in class, you'll have some data filled in here. And if you don't, I'm going to show you a way that you can collect some data. So this is your starting height in meters. And I'm going to collect some data using a website. So if you've collected data, you might want to skip this part because you won't need to do it. I've got a website here. It's just a bit of a simulation. And my head's in the way, I've just realized. I'll put it here. And like I said, you won't need to do this if you've already collected the data in class. And I've got the link to this in either the comments, or I've chucked it somewhere where you can find it. So what I want you to do, there's a lot of stuff here that we don't really need. So this is the basic kind of simulation here. Now you can see that this kind of marble or ball is just kind of going continuously. It's going forever. So I've played around with this a little bit. And what we're going to do, this bit here which says damping, we're going to put a value of 0.2 on there. And what that does is it's going to actually have a bit of an effect of, you know, some of these forces that slow it down, something like friction. Okay, and this is more like what we want. Okay, so now what we're going to do is the tab up the top, we're going to click on, so I was here on sim, we're going to click on time graph. And basically that's going to help us to collect some data. Now down here we've got line 1, line 2, line 3. Have it set up like me, so it says Y position, and then none and none for the other lines, okay? Now this looks a bit scary, but we won't stress too much about it. So what we're going to do to simulate our roller coaster is I'm going to get the ball, I can click and drag it, and I'll put it on a value for my height. So we'll pretend that the Y kind of axis is in meters, okay? So let's just say this is 4 meters, and I'm going to let that go, and you might have to press play down here. And it's going to kind of do some stuff with this graph. Now, you might have to click and drag here. So the 4 meters was where I started it, which kind of correlated with this 4 meters here. And then you kind of, hopefully you noticed it kind of bounced as the ball went up and down. So all I need to do now is basically get the maximum height that the ball rolled to, and that's going to be my finishing height. I don't care about all the others. It's just basically how far did it go and what was the finishing height, okay? Because that's basically what we're doing for our energy. So I'll need to approximate, so I can drag this really close to the axes. Now I'm going to have to approximate this. So 2.5 to 3, So I might approximate that as 2.8 meters, okay? So I'm just gonna go back to my Word document. So the starting height was 4 meters. I'll do 4.0, and the finishing height was 2.8 meters, okay? Now I have a feeling with this simulation, I'm just gonna get the same answer every single time, but we're just gonna do it anyway. So I'll put my ball there again. Now, was I recording? That's the real question. Okay, let's stop this. And play. Okay. Might go back to the start. Okay. So did you see what, I don't know if you saw what I did then, but I just pressed this button here and that kind of made it go to the start again. So I've done the same thing. I started at 4 and I want to see what my finishing height is. So I'll just press pause and then I can kind of click and drag, get this one, and then that's the height that I'm kind of looking at. So what do we think? To be perfectly honest, I'm not sure if there's a difference, but I feel like that's closer to 2.9 than 2.8. I'm just going to write that anyway. That's my kind of, that it's going to be random error in terms of what's your interpretation of that value, because you won't get it exact. Okay. So I'll go again, go back, and I'll go to my 4, and then I'll click play, and then it will kind of, okay, so it does the exact same thing. So in real life, when you collect your data, it's going to go a bit different. There's going to be a few more errors involved. A simulation is a bit more kind of, perfect. So we're going to get similar answers every single time. So the answer there is going to be 2.8 again. And realistically, this one was probably 2.8 as well. Okay, so that's my answer. Now, just bear in mind with your graph, with your, entering your tables, you don't put units in there, and make sure the starting height is in meters. Now, if you're doing this in the classroom, you're not going to get answers of meters because it's going to be less than 1 meter when you're doing your in-class stuff. So instead of 4.0, students in my class were getting 54 centimeters, for example. So 54 centimeters would be 0.54, okay? So you need to make sure your units are in meters, all right? So 0 point something, whatever the centimeters are. Okay, let's go back to this. So trial 1, trial 2, average. To calculate an average, I'll just get my calculator. That's going to be the numbers added and then divided by 3. So that's going to be 2.83333. So I'm going to round that off to 2.83. All right. I'm happy to keep my answer to 2 decimal places and then just have that consistent going down. Now, something really important here was the mass of the marble. We need to record that, okay? Now, the marble, I'm going to give an example of 5.55 grams. That was just one of the marbles in our class that I seem to remember for some reason. So 5.55 grams. In order to go grams into kilograms, because we need the mass of the marble in kg, we need to divide that by 1,000 because there's 1,000 grams in a kilogram. So I get 0.00555. So I'm going to write that there. Okay. Kilograms. So that's going to come into play a little bit later. Now I'm going to, I guess, I could keep going and collecting data, which I need to be doing. So you've got 3 different tracks. Now with your simulation, you can go back to the sim and you can change the tracks. So there's different ones, loop the loop. That is impossible. I guess we're doing the loop the loop. So we could do that in order to collect more data. I won't do that for the purposes of making the video as shorter than it needs to be. Okay. So I'm going to do this example for track 1. So here we've got our calculations. The starting height in meters, I had 4.0, which was from this table here. The starting GPE, now how do we do this? So GPE is going to be, and I'm just going to write it up here. GPE is mass times gravity times height, okay? And you're welcome to write down calculations on your sheet to show you working out. So the mass is the mass of the marble, which is 0.0555. Times by acceleration due to gravity, which is 9.8 meters per second squared on Earth. So it's always going to be 9.8. And then we've got our h, which is the height. So the height is 4. So we'll be doing that. So what is the gravitational potential energy of this marble? So that's based on height. So the potential for this to turn into another form of energy. So I get 0.21756. I'm going to round that off to 0.218. And my answer is in joules, because energy is in joules. So I'll make sure I put that unit in there, and I'll say 0.218. The ending height average you obtain from here, so that's 2.83. And I'm going to do the same calculation here, the ending GPE. Again, that's going to be in joules. So I can take this and I'll do a new calculation. And the only thing I'm going to change, so the mass of the marble stays the same, the GPE stays the same. The difference is going to be the ending height. So that's going to be 2.83. It's always going to be lower than this one here. So I can put that in my calculator once again. So I'll start from scratch. 0.00555 times 9.8 times 2.83. And that gives me 0.153, blah, blah, blah. I'm going to round that off to 0.154. Keep the decimal places consistent. 0.154. Notice that I'm never putting units in the table because you don't need to, because they're in the heading. So the change in GPE is going to be, so how does the energy or the gravitational potential energy change from the starting height to the ending height? So that's going to be a subtraction. You're subtracting this by this. So it's going to be 0.218 subtract, or take 0.154, and that gives me 0.064. Okay, and that's it. So basically it's saying that's the difference in GPE. Now, we know going from the beginning, the law of conservation of energy. Energy cannot be created or destroyed, only transferred or transformed. Transferred means it goes to a different object. Transformed means it's kind of can be converted to a different type of energy. So what energy has it been transformed into? The answer is kinetic energy, which is moving energy. So the law of conservation of energy, we can get that from the introduction. Now, when you write this, I would do a different color. So you can have your answers in, I don't know, blue. Transferred to another object, or transformed into another type of energy. Okay, I'm not going to answer all the questions, but we can do that. That's a quick Google search, easy peasy. At the lowest point of the path, the GPE of the marble is 0. What has happened to its energy? So this is the key concept here. So if I would go back to my kind of simulation here. When this goes down, it has GPE, maximum GPE. When it goes down, it speeds up, and that's when the GPE is being converted to kinetic energy, faster, 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 faster. And when it gets to the bottom, that's when its speed is at its highest, when it's right at the bottom, and the GPE is at the lowest, because if there's no height, then there's no GPE if something hits the floor, okay? Now, realistically, our roller coasters aren't really hitting the floor, but it's pretty close, so we're just going to kind of pretend that it does. So what has happened to this energy? So it's been transformed. Into another type of energy. So that's kinetic energy. What other types of energy though? If you can think of other types of energy, think of a roller coaster, think of other types of energy, light, heat, sound. Does a roller coaster make noise? If so, then there's been some sound energy there. So we can elaborate a little bit on that answer, but that's the key concept. So for track 1, state the kinetic energy that the marble would have had on the lowest point of its path. This is another key concept. Now, if the starting GPE, that's the maximum gravitational potential energy, was this number, 0.218 joules, we're assuming that the majority of that has been converted to kinetic energy, which is the moving energy, because that's the maximum speed. So the answer for this question, there's multiple things you could say, but realistically, it's gonna be this number or something close to this number. Not more, because we can't create energy. It could be a little bit less, because maybe you're taking into account that some of it might be lost to heat energy, sound energy, if there's sparks, light energy. But we can assume that there's 100% efficiency for the purposes of this task. Use the kinetic energy to state the velocity of the marble at this point. Ke equals half mv squared. Okay, so we've got the kinetic energy. So I'm just going to write that it's that. Now you should put an explanation down, but that's going to be my kind of key thing that I'm writing here. The calculation I'm going to base off of this. Now I'm going to do something with you guys because this is important. So Ke equals half mv squared. I'm just going to write this here. Ke, which is kinetic energy, equals half mv squared. We're going to rearrange a formula. I'll show you how to do it. So we want to get velocity because it's saying calculate the velocity of the marble at this point. So I want to get this thing by itself. Rearranging formulas is so important in physics. If you're doing physics or chemistry in stage 1, stage 2, you need to be able to do this. So it's good to get it done out of the way now. Inverse operations, guys. So velocity is multiplied by mass and by a half. So what I'm going to do is I'm going to divide both sides of this equation by half and m, because those are the factors that I want to get rid of because I want to get v by itself. So they cancel. Half and half cancel, m and m cancel. So what's left is Ke over half m equals v squared. Now I'm going to just rewrite that because you like to have, we read from left to right, so we want to have that on the left. It's the same thing. Okay, now v squared equals Ke divided by half times m. How do I get v by itself? I need to do the inverse operation of squaring something. The inverse operation of squared is the square root. So if I do the square root of this and the square root of this, I end up with, so you can cancel because they're the inverse of each other, you end up with v equals the square root of Ke over half m. Now, if you want to make it a little bit easier, you can multiply both the top and the bottom of this side by 2, okay? Essentially, what I'm doing is making this a little bit less awkward. So the same formula can be square root of 2Ke over m. That and that are the same thing. You're going to get the same answer. So that is going to be our formula for this. So plug in your numbers and you'll be able to figure it out. So the way I would do it is, now I don't have a scientific calculator here, so it's not as easy, but I would say 2 times kinetic energy divided by m and then put the square root of that. We'll see if this works. This could go completely wrong. So the kinetic energy is that. So I'll go 2 times 0.218 divided by the mass, which was where's the mass of the marble? Up here, 0.00555. 0.00555. That's my number. And then this is the part I'm not sure it's going to work. Take the square root of that number. Oh, it worked. Wicked. Okay. So my answer is 8.86. I'll just round it off there. Okay. Brilliant. So I get 8.86 meters per second is the velocity. Now I need to show my working out. So I would need to write all of my steps down, including my rearrangement. If you wanted to, guys, you could do something like this and screenshot it and then chuck it in here, paste it in there. And that would be a brilliant way to show working out, because sometimes just typing it can be a little bit awkward. Why was the GPE at the end of the runs less than the beginning? what happened to the lost energy? Guys, we talked about that already. Where did it go? Well, I mean, look, as you go down and then up, it doesn't go as high as it did originally. If I go back to the simulation, assuming I've got my damping thing on, it kind of goes lower and lower and lower. So where is that energy going? It's being transformed, guys. It's being transformed. So it's transformed to other energy types, and they would be heat, sound mainly, maybe light. There might be other forms as well, but they're the main two, heat and sound, okay? Calculate the efficiency of the roller coaster system for each of the 3 tracks. So you've got track 1 and track 2 and track 3. So guys, efficiency is basically saying, okay, that was the start in terms of energy, that's the end, okay? So we want to calculate an efficiency percentage. So I'll do track 1 for us. Oops. So efficiency is going to be the final GPE divided by the initial GPE times 100. So we've got 0.154 and 0.218. So it's going to be 0.154 divided by 0.218. And that's going to be, times 100. 0.154 divided by 0.218 times 100, 70.64%. And that's pretty efficient. So that means essentially 70% of the energy is being retained. So gravitational potential to kinetic, to gravitational potential to kinetic to make it move. And about 30% of it is lost to sound, heat energy, okay? That's a reasonably high efficiency percentage. And you can see in terms of how that efficiency changes. Now, guys, that's really important if you're someone that's designing something like a roller coaster, because you want it to be efficient. That's why roller coasters have the hills and then the steep descents and then the next bit goes up a little bit. And what a great explanation. It's really important to keep that efficiency percentage to reduce the costs if you were someone that was running a theme park. Rank your 3 tracks in order from most to least efficient. That's pretty easy because it's just looking at the percentages. Why do you think it's happened? Depending on what your tracks are, essentially the more kind of wavy they are, like this one, they might be less efficient, okay? Usually the more efficient ones are ones that have kind of littler loops to begin with. But you might have a different idea based on the shapes, okay? There might not be a right or wrong answer to that. As long as you show a bit of thought process behind that, it should be really good. What could be done to reduce the loss of energy in your roller coaster systems? The main source of kind of energy loss is friction. So the contact of 2 surfaces, okay, between each other. So the marble rolling in the tubing is going to affect that. So there's a number of things you could do. How could you reduce the friction between the tubing and the marble? Think of the materials they're made from. Could be maybe some different materials, some less grippy materials. Maybe there's some water through there. Think of like a water slide, obviously. That reduces friction. People fly down those. And there's other answers as well. Maybe the size of the tubing. There's lots of things you could talk about there. Guys, thanks so much. If you made it to the end of this video, congratulations. I didn't think it would be that long, but we got there in the end. Good luck with your work, and I will see you next time.